about implications of the LHC Higgs results for supersymmetry.
So, thank you for the invitation to come here. So my plan was to discuss the implications of the LHC Higgs results for supersymmetry. And in fact, my plan was to stick to the minimal version of supersymmetric extension. I mean, I was not planning to do the whole job and talk about the entire full-fledged supersymmetric theory. So I'll stick to the minimal supersymmetric extension of the standard model. And my plan was, after discussing, just introducing briefly this MSSM scenario, is to discuss the applications from the LHC results. The first application comes from just the measurement of the mass, the fact that the Higgs mass, the one that has been observed, has a mass of 125 GeV, has really profound applications for supersymmetry. From the Higgs couplings, in the sense that the measurement of the observed Higgs couplings to gauge bosons and fermions also puts constraints on the supersymmetric parameter space. Then there are implications from the search of the other particles that are predicted by these theories. In fact, they have extended Higgs sectors, so there are additional Higgses that one has to search, and indeed they have been searched for, and some limits have been set on that. And then some conclusions. But then during the coffee break, I've had the coffee break, the coffee after lunch, we had a small discussion with a few people, and maybe it was interesting, in fact, to start with some general introduction to give some general implications of this Higgs discovery, and not only in the context of supersymmetry, but maybe even in the case of the standard model. And this is what I will start to do. Okay, so maybe I will just be very brief here, because you have heard the story many times, I guess, since a few years. So the Higgs mechanism was basically sold to us a few decades ago as the mechanism to generate the masses of the W's and Z's and also the fermions in a kind of SU2 cross U1 invariant way. And the trick was to introduce an additional complex scalar doublet field into the SU2 cross U1 Lagrangian, write something that it's SU2 cross U1 invariant, and in fact the general potential, the most general potential that involves this field and that is SU2 cross U1 gauge invariant involves in addition to the kinetic term, which involves the covariant derivative, you have something that is a mass term and something that is a quartic interaction, basically the usual thing that you expect for a scalar field. And the trick is, in fact, to have a minimum that is not at phi equals 0, but shifted somewhere. So you have, in fact, a non-zero vacuum expectation value. And this makes that while the theory is symmetric, in fact, the vacuum is not. And at the end of the day, if you try, in fact, to reinterpret the whole theory while sitting on this vacuum, you will realize that, in fact, the 3 degrees of freedom among the 4 that you put in the beginning will be absorbed by the longitudinal components, in fact, to form the longitudinal components of the W plus, the W minus, and the Z boson. And you have longitudinal components, that means that you have basically have masses. Okay? And the beauty of the standard model is, in fact, that with this same Higgs doublet, the beauty, in fact, the simplicity of the model is that with the same doublet and its complex conjugate, you can basically just construct a kind of Kawa-type Lagrangian that generates for you immediately the fermion masses. So with the same field, you generate both the gauge bosons and the fermion masses. Okay? So you have one residual degree of freedom, and this residual degree of freedom corresponds to a spin 0 particle. So the particle that is left over is under parity and charge conjugation 0++ state. It has a mass that comes immediately from the scalar potential, and it links for you lambda and v squared. Lambda is the quartic coupling, and v is the vacuum expectation value, and the vacuum expectation value basically is given by the Fermi constant, so it's fixed. So in fact, it's the only free parameter in the theory. The same mechanism that gives you the masses also gives you basically the Higgs couplings to fermion and gauge bosons. So in fact, they are fixed in the theory. And the self-couplings also come basically from the scalar potential, so they are giving in terms of the Higgs mass. Okay? So because V is known, the only free parameter in the model is the Higgs mass. Okay? So that's really the simplest extension and the most economical extension that you can imagine, I mean, to address this mass generation question. Now, of course, before the launch of the LHC, we had some information on this mass, although it was a free parameter, but in theory it had to have some, some values that obey some boundary conditions. The first ones are experimental type. In fact, one big one comes from the high precision measurements that were performed for 20 years before LHC started, and which for many years, in fact, from the discovery of the top quark, and we knew that the top quark had a mass of 175 GeV, the Higgs mass immediately came out to be something like 100 GeV, and it stayed 100 GeV for 20 years. So it was kind of prediction from the very beginning that in the context of the standard model, if you don't assume any new physics beyond the standard model, the Higgs mass has to be something around 100 GeV plus or minus 30 GeV with the 95% upper limit of 160 GeV. Okay, so we knew that the Higgs should be light. Then from direct searches at lab, we also had enough in center of mass energy to produce the Higgs, and because we didn't observe anything, the limit was 114 GeV from lab. And Tevatron started already to be sensitive to the Higgs. There is a story about it, but I will not go through it. Tevatron started to be sensitive to the Higgs just before the launch of the LHC. So there was a little bit of competition in the beginning. Now this is for the experimental part, but we had also some, because this will be important for later, we had also some kind of theoretical prejudice about the validity of the standard model once you increase the energy range, and you impose that the model is valid up to this energy range. Okay, so you need, in fact, to have a theory that is unitary, and you know that without the Higgs, the theory is not unitary because the amplitudes for longitudinal scattering, for longitudinal vector boson scattering grows like the energy squared, so you had something to regulate it, and the thing that regulated it, in fact, was the Higgs channel. Yeah, so you had one contribution in the S channel, but also one contribution in the T channel, and in fact, in order to make that the terms that are proportional to E squared completely disappear, you needed, in fact, to have a Higgs mass that is less than 700 GeV. Otherwise, the amplitude still grows out. Okay? So theory is unitary only if the Higgs mass was a small 700 GeV. And this was an extremely important information, in fact, because we knew that either the Higgs was there, for the LHC, yeah, that was, and in fact, this is exactly one of our main next problems, because at the LHC, we had a kind of energy scale at which we were sure that something will happen. Either the Higgs was light, 700 GeV, and in this case we will produce it, or it was heavier, and in this case the theory, in fact, will, the unitarity will be broken, and something had to be there in order to restore unitarity, and this something had to be at the scale of 1 TeV, and therefore it was also accessible at the LHC. So we kind of had a machine in which there was a kind of no-lose theorem where basically we will find something. And unfortunately, this is basically the last machine where this the fact that we are sure that we will find something will happen. Okay. So, for instance, this 100 TeV machine that we were talking about during, it's not clear whether we will find something there. We are guaranteed to find something there. Anyway, the other big argument for light Higgs and for not two light Higgs in some sense is the triviality of the fact that the quartic coupling, the coupling, the quartic coupling in the scalar potential, in fact, evolves with energy, so it receives some radiative corrections from different particle contributions. In fact, the heavy contributions in the game, which are basically the W, the Z, the top, and also the Higgs itself. And this coupling, in fact, evolves with the energy, and at some point, in fact, in the evolution, you just basically hit a lambda pole. If this coupling is big, you remember that lambda is proportional to Higgs squared, so if Higgs is big and lambda is big, at some point, the radiative corrections made that it exceeds by far 1, it goes to infinity, and therefore you have to avoid that, and to avoid that, in fact, is to force the tree-level value to be small enough in order not to evolve too high. And the other thing is, in fact, more important, is the fact that to have a scalar potential that has this Mexican hat shape, you need that the coupling lambda is positive. Otherwise, if lambda is negative, the potential basically, extreme thing would be that the potential is reversed, and therefore you don't have a minimum because the minimum is sitting at minus infinity. The potential is not bounded by below, from below. So you really need to have this coupling positive, and it happens that you had contributions from the top, from the W and Z that interfered distributively, and the top contribution could make that this coupling goes to zero. Okay, enfin, goes to zero and becomes negative. Anyways, at the end of the day, it puts you in a lower bound on the Higgs mass. And this lower bound is 70 GeV if the cutoff at which you stop the standard model, I mean, and you expect new physics to appear, is 1 TeV. And if you go up to Planck scale, this cutoff, this limit is 130 GeV. And this is the famous, whatever it's called, the Roman plot or whatever, where you have lambda, M Higgs, if you wish, in terms of the cutoff lambda. And the good Higgs mass range is sitting between the two lines. So for cutoff of 1 TeV, you have a Higgs which is between 600, say, and 70 GeV, 770 GeV. And if you go to very high scales and to the ultimate scale, the Planck scale, you see that the Higgs should be sitting in a very narrow range, 130 GeV to 180 GeV. So we had, in fact, two good arguments to believe that the Higgs would be light. We had this one from high precision measurements, and from our prejudice that unification should be somewhere there, we knew that the Higgs mass would be also kind of light. So that was before in the context of the standard model. But we knew, and we know it. Still, we know that the standard model cannot be the entire story, and for immediate and basic reason. First, you have to include the fact that the neutrinos are massive, because in the standard model you have only left-handed neutrinos, and the left-handed neutrinos are almost massless. You need something in addition to the standard model in order to generate the neutrino masses. But it has some other problems. It doesn't have enough strong CP violation and to have baryogenesis to explain the baryon-asymmetry in the universe. It doesn't incorporate gravity, the usual. And then, just from the Higgs sector, remember that to have this Mexican hat shape for the scalar potential, in fact, you needed to make that the mu squared term of the potential, the mass term, is negative. And the mu squared term negative is not really, it should be a mass, so it's a kind of tachyonic-like mass. It's not really natural. So there is no, in the standard model, it's really put ad hoc, and there are extensions, in fact, where it comes out naturally. Now, the main problems that call for, at least from the theory level, that call also for higher extensions of the standard model is the fact that if you really believe in the unification paradigm, this doesn't work in the standard model because the couplings and the gauge couplings do not meet at a given scale, and therefore you cannot really embed the standard model, three subgroups of the standard model into a unification group with one coupling constant. You have the dark matter problem, so you need really a stable, neutral, weak, and massive particles to account for it. And above all, and this is basically the paradigm or the wish or whatever you call it, that has driven us for 40 years in order to construct extensions of the standard model. This is the hierarchy problem. The fact that if you start to include radiative corrections to the Higgs mass, you find quadratic divergences, and so that means that they are proportional to the cutoff squared, the lambda squared. And if you want really to go up to very ultimate scales, then that means that the Higgs mass has the tendency to be close to this high scale than to the electroweak scale, in particular that you know that the Higgs mass should be of the order of few hundred GeV in order to have some unitary theory, etc. Okay? So you really have a problem with the scales. And I will not go far in there. I'll just give you the three big avenues for solving the problem. The composite avenue, in which, in fact, you just decide that this is a problem related to the fact that the Higgs is a spin zero particle. The problem doesn't occur for gauge particles because there is gauge invariance, which protects the gauge boson masses. Chiral symmetry protects the fermion masses. There is nothing to protect the scalar masses. So let's forget about fundamental scalars and therefore make the Higgs that the Higgs is a composite object. So the Higgs is a bound state of a TT there, say. Fermion anti-fermion bound states. The second solution is to say that, okay, in fact, why should I go to the Planck scale? imagine that in fact the effective Planck scale is at the scale of 1 TeV, and in this case my cutoff is low enough in order to have naturally a Higgs mass of 100 GeV. And this is what we've done in extra dimensions. In extra dimension scenarios, you have in fact the effective gravity scale in the fifth, in 5 dimensions, for instance, is really 1 TeV. So you don't have to go beyond that, and therefore you are not really hit by the problem with the cutoff. And of course, in this type of models, in fact, you have also ways, in fact, to break the symmetry without referring to any Higgs. And in fact, you can make, in fact, Higgsless scenarios in this models. And of course, you have the supersymmetric version that is that I'll try to talk about in the following. And at least in the context of the Higgs sector, in fact, for me, there are really two very interesting ingredients. The fact that you have naturally mu squared negative. In fact, it happens that at high scale, this Higgs mass squared is positive, but it receives radiative corrections from, in particular, from the top sector and the supersymmetric partners of the top quarks, which have very strong couplings to the Higgs. And this particle basically makes that at some point, which is a few hundred GeV, the mu squared becomes negative and therefore triggers for you electronic symmetry. Well, that's for one thing. And the second thing is that, of course, you have at least in the Higgs sector, you have, you have unification of the gauge couplings, you have dark matters, and in this case, at least for the Higgs sector, you need, in fact, 2 Higgs doublets in order to generate in a kind of consistent way the masses of the up-type and down-type fermions, and this leads to 5 states, which makes that you have a richer Higgs spectrum. And of course, these are only avenues, and the idea before the LHC started is that, okay, each avenue had its own big possibilities, and each possibility had some sub-possibilities, and at the end of the day, you ended up with a big list of all possible scenarios. And the choice had to be made by an experiment, and the LHC was supposed to do the job for you. The only thing is that maybe the LHC did a too harsh job, and at the end of the day, from all these possibilities, in fact, it looks like, once the Higgs was discovered, it looks like basically, at the end of the day, only one possibility is left, and it looks like the standard model Higgs. You know, in fact, we didn't have really to do all this, detours, in fact, to look for extensions. At least the ones that we have observed is the standard model Higgs. Okay. Now, before getting to that, but let me say first some kind of words about the fact that at least we have discovered the Higgs, so it's a big achievement, and maybe we should not downsize this discovery. For me, it's really something that maybe we should be proud, because after all, we knew that the simplest model that we had on the market. We knew for many years that in fact the Higgs mass should be, in this simple model, the Higgs mass should be something like 160 GeV, 100 GeV plus or minus 30 GeV. And okay, you make the experiment, you measure the mass, and you find something like 125 GeV. And of course, this expectation was coming from, of course, quantum correction, so it's really precision measurement of the permeable level of a model that you think is correct. And these corrections are coming from really quantum fluctuations. So at the end of the day, you basically are checking, in fact, this theory at the 10 to the minus 4 level, and you are checking the quantum correction and the quantum structure of the theory. So it's really a big thing. So we should be we should be slightly, we should make propaganda for it. It's really impressive. Now the problem is that, of course, when you look at the rates for the Higgs, you know this is what the usual propaganda plots of Atlas and CMS, but this is not updated because this is pre-summer numbers. So at that time, things didn't go yet even more standard model like, because as we was discussed, the coffee break. In fact, now CMS has mu equal 1, exactly 1. So. Okay, but anyways, you see that this is the couplings, in fact, the strength of the couplings to gauge boson and to fermions compared to the standard model expectation. And basically, 1 means that the coupling is standard model-like. And if you combine Atlas and CMS, now it's almost 1. Right? Okay. And on top of that, there is no particle that has been produced in addition, no other Higgs, no other supersymmetric particles, no Kaluza-Klein state, no composite quark, nothing. Okay? So we really have in a kind of standard model-like situation. So what should we conclude from that? Many people, in fact, start to think that, after all, we have maybe the theory of everything. Yeah. First of all, we have a theory that is theoretically very nice. It is renormalizable, it is unitary, it's perturbative, and it's perturbative up to the highest possible scale, because you can extrapolate, in fact, the theory to the Planck scale, in particular, because of this limit that you have from stability of the electroweak vacuum. It happens that you are really close to absolute stability of the electroweak vacuum. In fact, at the Gat scale, or at the Planck scale, you have a coupling that is almost 0, and even this derivative is 0, so it looks like a fixed point. And, well, in fact, you can even push the extrapolate the standard model up to the Planck scale, and at that scale, link it basically to gravity without much efforts. So in fact, you are really in a theory that is not only very successful in describing all the present, all the data, but on top of that, it can be extrapolated to the highest possible scale. Okay. Now, for the little problems that had and that we, in fact, for which we needed to have some extensions, in fact, there are nice and easy patches. Okay. In fact, you don't have to go to some radical chance in order to fix a few problems of the standard model. Okay? For instance, for dark matter, it's clear that the first candidate for dark matter was already proposed 30 years ago by Petchy and Queen, who in fact addressed a different problem, which was the strong CP problem. And for the explanation of this strong CP problem, needed an additional particle that is the action. And this action, in fact, can be a good candidate for dark matter. It's not as sexy as, for instance, the neutralino, but because it has no thermal, it's not the thermal relic, in the sense that, it's not in thermal equilibrium, the decoupling temperature, etc. But still, it is a candidate for given ranges of this mass and for its mass and its coupling. So it's still a good. And this is for me a standard model-like particle, because just need to add an additional U1 symmetry that you break, and it's not that different from a standard model. Now, for the neutrino masses and for the Bion asymmetry of the universe, in fact, there is an easy solution, which is the existence of right-handed neutrinos, in which there is some CP violation. This CP violation will trigger some lepton number violation that triggers the Bion number violation. This leptogenesis scenario for biogenesis. And all this, in fact, can be done at the scale of 10 to the 10 GeV, 10 to the 11 GeV, without any problem. In fact, people already advocated the possibility of having an SO10 symmetry. And in SO10, you have a fundamental representation of dimension 16. You can put all the standard model kind of fermions, plus there is still some space for a Majorana neutrino. And this Majorana neutrino basically does all the job for you. Okay? And what happens is that because you have an intermediate scale at 10 to the 11 GeV, in fact, you can basically change the slope of the evolution of the gauge couplings at this particular scale in order to make that at the unification scale, all this coupling unified. So in fact, you can even address the problem of gauge coupling unification in the context of SO10 with some small, some intermediate scale. So in fact, you can address basically all the problems of the standard model by just doing a very small extension, which is unification with the scale, intermediate scale at the of 10 to the 11 GeV, for instance. This is one example, so I'm not really telling you that this is the only possibility. So you really can extrapolate the standard model just slightly in order to address basically all the questions, except, of course, for the big question, which is the hierarchy problem. And now, the hierarchy problem now is becoming a big issue because, after all, we are starting, in particular, because we are not observing the particles that come with the extensions that have been advocated to explain, to solve this hierarchy problem. People are starting to consider, to think that maybe we are asking the wrong questions. After all, maybe there is something that we don't know about, and this hierarchy problem looks basically like a kind of fake. But, well, people now are starting to ask questions. But anyways, in the context of all this, three big avenues that I was discussing in order to solve the hierarchy problem, it's clear that all call for a scale that is pretty low, 1 TeV at most, and it happens that the fact that we have observed only 1 Higgs and we didn't observe any new particle, and on top of that, this Higgs looks like standard model-like, and therefore all the deviations beyond the standard model should be small, and which means also that the scales related to these deviations are large. In fact, all this potential, all these extensions are in trouble. In particular, anything that is strongly interacting was already kind of squeezed by the experimental high precision experimental data. But you could evade most of this data by doing some patches and by making the theory slightly less strong. Here, in fact, I think the situation is becoming a little bit critical. In particular, this is also the case for extra dimensions, where in fact the cutoff was supposed to be 1 TeV in order to explain the fact that the Higgs has a mass of 100 GeV. But now, in fact, because of these high precision measurements of the Higgs mass, the cutoff should be at least 10 TeV. So there is already a little hierarchy, and therefore you are not really in a kind of very nice model in which you have only one big scale above and this that's it. Here you really clearly you have a little gap. And this is in fact also a problem with supersymmetry, because in fact, in order to have a very natural theory, you need superpartners and particular squarks and gluinos that are at a few hundred GeV scale. And it happens that not only from the present searches on these particles, but also from the precision measurements of the Higgs properties that I will discuss now, this scale is not anymore a few hundred GeV, but it's at least 1 TeV. And this is a little bit problematic in the sense that we are getting we are starting to be a little bit squeezed and not very at ease. So happens. I mean, it's maybe that's just that nature is a little bit fine-tuned, but okay, we'll see that in the last discussion.
Can I just make one comment?
Yes.
So I'm certainly agreeing with all the broad things, and this definitely looks like a Higgs. But I would like to just this one point you mentioned about strong dynamics. I mean, in particular, I think Nima was the first one to declare technicolor dead, right? Nima Kani-Hamed.
The first time it was declared dead was by Peshkin and Takyoshi in the late 80s. Okay.
Some bugs were, this time around, the second dead. So, but to me, I mean, his argument is completely senseless, because his argument is that this is a victory of weak coupling, right?
Yes.
So if you take some state and measure its weak couplings to other states, then you will find that those couplings are weak couplings, and we've done that, right? You have a state and you look for its couplings to WW and so on. But even if the state is strongly coupled, they will always be weak, because otherwise the theory would not make sense as an electric symmetry. So my point is just that that is not enough. I mean, if once you measure the self-coupling, even that I would say in general you cannot be too sure, but that would certainly help. That's a coupling where you can really probe the nature of this state, right? That is nothing. I'm completely agreeing that the data clearly looks like this. It's becoming more and more standard about things like that you cannot get rid of.
I remember in the late 80s where labs started in fact to do the precision measurements, and everything looked like the standard model scenario. Is that you see in this strong interaction theories, in fact, for example, in Technicolor, not only the fact that there was strong interaction, but in fact there were many states that could have contributed to this high precision measurements. For instance, imagine the fact that you have a large number of fermions in the game would have added anyways, even if they didn't couple strongly, even if they have a weak coupling.
But you don't in all technical.
Yeah.
But I completely agree in the ones where you have a lot, yes, those were killed already for that.
So, it's... and now, for instance, with the Higgs, it's clear that, for instance, I told you, compositeness for me, anyways, it was interesting mostly for the Higgs sector because I would have evaded in this case the possibility of having a fundamental scalar.
Yeah.
Here it's clear that it should have been much heavier than 120 GeV. Okay. You can, of course, now fix it, but it's not. You start to make a kind of the constructions.
I agree.
Not only in this case, but in fact, in all cases, the constructions are starting to be a little bit baroque. You know, it's.
I mean, if I can comment, it's not completely true, right? So, because I mean, one of the things which is new in this game of compositeness and compositivity is also the lattice studies have been made, right?
Yeah.
To understand this issue, if you can have light composite scalars in strongly interacting models, right?
Yes.
And there are many groups now around the world. I mean, we have one, but there are another one in San Diego, another one in Germany. I mean,
So
and
you can
Japan
have
as well. So it seems that you can have, you know, large separations between scales, because I mean, you have some angles, right, which you can tune. I mean, on top of that, you can also have AX, which is a composite and is mostly, for example, a pseudo-Boson boson, like in the
Clearly. No, clearly. Mm-hmm.
And these two things don't exclude each other.
Yes.
For example.
Yeah.
So
But
I wouldn't say, and I agree with you that if you have a lot of fermions, you're basically excluded, right? But you can do all this with just two fermions. Yeah.
Okay, well, let's. Anyway, so that was just a big introduction, of course, because maybe it's so it was not as short as I would have liked it to be. But okay, let me now just tell you about what the meaning of all this precision. I mean, all this discovery of the Higgs and all the measurements that have been done on the Higgs in the context of the minimal supersymmetric extension of the standard model. And here, let me briefly just describe for you the model. It has two Higgs doublets, so 8 degrees of freedom. So if you really want to generate the masses of the up-type and down-type chiral fermions, you have really to do it this way. And this means that you have 5 physical states. Once you make 3 to form the longitudinal components of the W plus the B minus and the C. 2 CP even Higgses, 1 CP odd, and 2 charged scalars. And the simplicity of this minimal supersymmetric extension of the standard model is that, in fact, the 6 parameters that you have in the game, in fact, you have 4 masses and 2 mixing angles. You have tangent beta, which is the ratio of the 2 vacuum expectation values of the Higgs fields, and an angle alpha that diagonalizes the CP even Higgs sector. In fact, you have 6 parameters in a general, if you had only a general 2 Higgs doublet model. In supersymmetric scenarios, in fact, there are strong constraints which make that at the end of the day you have only 2 free parameters. So 2 free parameters starts to be an interesting theory. So once you fix 2 parameters, and these are in general taken as this tangent beta, I said, the ratio of the 2 vevs, and the pseudoscalar Higgs mass, the CP even Higgs masses are given simply, the charged Higgs mass is given in terms of MA and MW, and the mixing angle by this simple formula. So, very, very simple situation. And on top of that, you have an upper bound on the Higgs mass, which is mz cosine 2 beta at 3 levels. We will see that there are indeed some radiative corrections. And then you have 3 Higgses, which are almost degenerate in mass, with masses of a few hundred GeV up to the TeV scale. Okay. Now, a good feature is that these 2 CP even Higgses have to share the coupling of the standard model Higgs, in particular to VV, to gauge bosons, W's and Z's, and the CP odd, because of CP invariance, doesn't have couplings to W's and Z's. And concerning the couplings to fermions, in fact, the couplings are given here, couplings to gauge bosons, couplings to up-type and down-type quarks. This is small h, capital H, and A. And you see that there are combinations of alpha and beta. And you see that, in fact, in one limit, which is this Higgs mass, one pseudoscalar Higgs mass going to infinity, you have 3 Higgses which become very heavy, 1 which stays light, and this light Higgs has basically, these are couplings normalized to the standard model situation. So you have couplings that are almost standard model-like. Okay? So this limit, which is called the decoupling limit, the MSSM Higgs sector reduces to the standard model Higgs sector with the light Higgs. Okay? And the couplings of H and A to gauge bosons are 0. This is why we call it decoupling. And in fact, it happens that the couplings to up-type quark are inversely proportional to tangent beta. The couplings to down-type quarks are proportional to tangent beta. and this is the same as for the pseudoscalar. And this tangent beta is supposed to be a parameter that is larger than 1, because it's basically related to mt over mb, so it must be bigger than 1. And it happens that for large values of tangent beta, these couplings are enhanced, so couplings to bottom and top tau leptons basically are enhanced, while these guys are suppressed. Okay. So this is all what I will say from this side. And the only thing I would add is that, of course, this situation is a little bit simplistic, because you know that it has been realized that radiative corrections have a very big role, in fact, in this game, and therefore you have to include them. And in particular, there are corrections that are extremely large. In fact, they come like the 4th power of the top quark mass. They are logarithmically dependent on the SUSY scale, and the SUSY scale here is basically defined as the geometric average of the two stop masses. You have a mixing parameter in the stop sector that also enters the game, and therefore this makes that these are big corrections, and in this case you have really to include them in the previous formulas that I have shown you. So you really, there is a big, it's a big field of work. People, in fact, went to calculate the 3-loop radiative correction in the Higgs sector. I will not really discuss about it. I will just tell you that it's a big story, and I will not quote it. So let me just now start by giving you the implications of the LHC Higgs results for the MSSM. The first thing is that if you see the formula, if you have seen the formula before for the radiative corrections, which is in fact given again here, you see that in fact you start from mz cosine 2 beta, which is basically mz. In fact, in the decoupling limit where ma is larger than mz, much larger than mz, and tangent beta large, which means that this cosine 2 beta is basically equal to 1, you see that m Higgs is only, the upper bound on m Higgs is basically mz. So the difference between mz and 125 GeV, which is 35 GeV, has to come from radiative corrections. So the radiative corrections is given by here. So you really need to maximize this radiative correction in order to get to 125 GeV. Okay? So first you need to maximize the tree level. So that means that you have to make yourself in the decoupling limit, and may go into a few TeV, or a few hundred GeV, 1 TeV. Large values of tangent beta to make this equal to 1. So tangent beta equal to 10. And then you have to go to make this radiative corrections very large. And to make it very large, you have two ways. You have to maximize this term, and the maximum of this term is reached when this xt is equal to square root of 6 ms. And then you have to make this logarithm as big as possible, and to make the logarithm as big as possible is to make that the SUSY scale is as big as possible. A few TeV here. And here starts the problem, because you know that you introduce a supersymmetry to solve the hierarchy problem. So your SUSY scale was supposed to be a few hundred GeV, the same order as the electroweak scale. And here you need, in fact, a SUSY scale that is large in order to achieve 125 GeV. Okay, and this is basically that. This is, I mean, you then say, okay, now the maximum that I will allow for this. You know that this fine-tuning measure is kind of subjective measure, yeah? I mean, it's a matter of taste whether you accept 300 or you accept 1 TeV or you accept 3 TeV. But for sure, the maximum that many people are willing to accept, are ready to accept, is a few TeV, which is basically the limit at which you should observe supersymmetric particles at the LHC. For me personally, if I don't observe supersymmetry next year at the LHC, which means that the SUSY scale should be something like a 2.5 GeV, I will give up, because that means that basically there's, the next chance for us to have supersymmetry available will be the 100 TeV collider we were discussing about this morning, and this will be basically out of my lifetime. So I'll stick to a situation where the SUSY scale is at most 3 TeV, and hoping that next year something will happen. Now, of course, this is just what happens if you just take into account the leading radiative corrections, but if you do a proper job, and many articles and many people did this proper job of including all the contributions of all the parameter space of the minimal supersymmetric extension of the standard model, in particular in this called phenomenological MSSM, where there are plenty of parameters that enter in the game, and they can be freely tuned. They are free parameters, so they can be freely tuned in order to maximize its radiative corrections. And there is also one ingredient, is that the radiative corrections, in fact, has some intrinsic uncertainty because you know that you have to calculate things in a perturbative way, and depending to make a perturbative calculation, in particular for radiative corrections, you need some renormalization. To make a renormalization, you need a renormalization scheme, and to meet when you truncate your perturbative series, what happens is that you can get different results if you use different renormalization schemes. And basically, the difference, but you know that in the exact, if you sum all orders of perturbation theory, the normalization scheme doesn't matter. It's just a trick, basically. So it should not matter. So at the end of the day, you should have the same results when you use two different normalization schemes. But this only happens if you sum the whole perturbation series. But because you are truncating, you find different results. So in fact, the difference is basically a reflection of the contribution of the higher order terms. So this is basically an intrinsic uncertainty because you have truncated your perturbative series. And these corrections, in fact, have been calculated in different schemes, in particular in the DR bar scheme, which is a dimensional reduction scheme which preserves supersymmetry, in fact, and the on-shell scheme that is usually used for electroweak physics. And, in fact, the prediction that you make for the lightest Higgs mass is basically a few GeV, 3 GeV. So you can consider that this 3 GeV is more or less the uncertainty that you have in the game, and therefore, you know, when you target getting a Higgs mass of 125 or 126 GeV, in fact, what you are targeting is something between 125 or 126 plus or minus 3 GeV. Okay? So the results that I will show you here were given in the very beginning when the Higgs mass, the best value for the Higgs mass was 126 GeV. So the target, in fact, what you should reproduce in the context of these models is a mass between 123 and 129 GeV. Okay? And this is the money plot, the thing that you obtain, in particular, in the two parameters that are most important for the radiative correction. This is the SUSY scale and the parameter, the mixing parameter xt. So this is the Higgs mass with this band between 126 and 129 GeV as a function of the xt parameter divided by ms. And this is for two values of the SUSY scale, 1 TeV and 3 TeV. Values, this is a scan, in fact, a scan of the parameter space with 1 billion scan points. I will not go through the details, but in fact, all the other parameters of the theory are varied. Okay, and these dots are basically what you get in this infinite number of large number of models. But I mean, the conclusion is in fact pretty clear because you see that for a scale of 1 TeV, you still have the possibility of having a Higgs mass of 125 TeV. The only thing you need to do is to fix xt to the maximum, to the value at which the Higgs mass is maximized. This is basically square root of 6 of ms. Okay, so in fact it's here. So in fact, you really need, if you have a scale, a SUSY scale of 1 TeV, to be in the kind of scenario in which the stop coupling, the xt coupling, the xt parameter, the mixing parameter in the stop sector is basically fixed to its maximum. And here, in fact, some people start to say that it's somehow kind of fine-tuning issue also. But anyways. Now, if you push now the scale, I mean the SUSY scale up to high masses, few TeV, 2 TeV, 3 TeV, then of course you are a little bit more relaxed. And at the end of the day, indeed, you can get any mass should fit, except maybe zero mixing, where there is basically xt equal to 0. You cannot get into this ballpark. But for any non-zero value of the mixing, you can get the Higgs mass that you want. Okay?
Can you still get like electroweak baryogenesis within this model?
I don't know. In the MSSM, no, because for electroweak baryogenesis, you need two things. You need a lighter Higgs than 125 GeV, and you need also a light stop, 100 GeV stop. And this SUSY scale, I discussed it, is basically defined as being the average of the two stop masses. Okay? Where is it? And therefore, you need to have of course, you need to have one. M-SUSY is equal to 1 TeV, so which means that if one stop is 100 GeV, the other should be 10 TeV also. And this is a little bit problematic. And on top of that, any mass that is smaller than the top quark mass for this stop one squark is basically excluded from direct searches. So in fact, you cannot have light stops. You don't have a light Higgs, and therefore you cannot have enough. You cannot make baryogenesis in this type of scenarios. Now there are people, of course, who are discussing the next minimal supersymmetric standard model in which you add a singlet, and in this case, many of these constraints are a little bit relaxed, and you can indeed have a chance of, because you can make, in fact, the Higgs mass bigger without the need of larger radiative corrections. So you can have still the possibility of having light stops. And you can maybe basically make a strong enough phase transition in order to make that baryogenesis occurs. But not in the MSSM, unfortunately. Okay, so that's the end of the story. The only thing I should say is that, as I said, this M-SUSY scale is supposed to be the average stop masses, I mean the geometric average of the stop masses. So it doesn't have anything to do, in fact, with the other supersymmetric particles. For instance, indeed, this M-SUSY is basically given like kind of like the squark masses. Okay, so it's clear that indeed this squarks should be basically 1 TeV, and M-SUSY 1 TeV. But still, you can in this stop sector still you can have a balance between the stop 1 and stop 2. Maybe not too big one, but you can have still a balance that allows you for stop masses of the order of a few hundred GeV. Okay, so it's still worth playing the game of searching for stops of a few hundred GeV, although the direct limits start now to be a little bit more severe. But anyways, the squarks are clearly above, I mean, in the 1 TeV range, but all particles that are only weakly interacting, like the leptons, the charginos and the neutralinos, which are mixtures of Higgsinos and gauginos, the supersymmetric partners of the gauge bosons and the Higgses, in fact, do not have anything to do here, and these, in fact, have really weak couplings, so very small cross sections at the LHC, and therefore, basically, the limit on these particles, on the masses of this particle, is still at the 100 GeV level. Okay, so you can really still have very light, electroweak, weakly interacting supersymmetric particle. Although here also some direct searches start to probe the few hundred GeV. Okay.
Can I just ask a quick question? What is the? This is only the implication of the actual mass measurement. So what is tan beta if you have 1 TeV? So you say you can have down to 3. If the scale is 3 TeV.
Alors, indeed.
Because this
If you, yeah.
Almost, I mean, will actually be checked by the Higgs bottom and tau branching.
Yeah. I'll come, exactly. You are right. I'll come to that. But this is the naive conclusion that you get just from the measurement of the mass. Huh? Well, in fact, I will show you that tangent beta equal 1 is still possible if you just relax a few other things, in particular. Here, what it means is that you can, in fact, make that this term is so big that you don't have to make this 3-level value, just saturate the 3-level value. You can make the 3-level value smaller and generate basically a larger radiative correction in order to get to 125 GeV. If tangent beta is equal to 1, in fact, this term is 0. And you generate all the mass, the Higgs mass from radiative corrections, and in fact, you can do it. But still, the price you have to pay is that you need M-SUSY to be of the order of 100 TeV or something like that. Yeah. But still, technically, it's possible. You just need, to reach values of tangent beta that are very low, you just need to increase the SUSY scale up to values that probably are unacceptable for everybody, but still, technically, you can do it. Okay? And for a scale of 3 TeV, you can still survive with tangent beta values of the order of 3. Okay? And this we come back to it because indeed, there are direct limits in which, in fact, you have tangent beta is constrained. Now, coming back to the constraints from the Higgs mass, what I discussed before was in this phenomenological MSSM, in fact, where you have plenty of free parameters. In fact, when you count everything, you have basically 20 parameters, because the only thing we require, in fact, in this phenomenological MSSM is that there is no flavor changing electric currents, there is no additional source of CP violation, and there is universality between the first and second generation to cope with some heavy quark physics. Okay, so basically non-diagonal mass matrices, coupling matrices for the squarks and the leptons, and basically no additional CP variation beyond the CKM. Okay, it makes that at the end of the day you have 20 parameters, but 20 parameters Okay, it's always for big numbers, so you can tune things in order to maximize the Higgs mass from all sources. Now, of course, for supersymmetry, people in fact like supersymmetry because of not of this phenomenological MSSM, but because of the unified models. There's models in which, in fact, you have only a set of free parameters at the high scales, and everything comes for free by just renormalization group equations. This is basically what happens in the minimal supergravity model, where you have a scheme for SUSY breaking, and this scheme is basically hide your ignorance in a hidden sector. In fact, you just say, okay, supersymmetry is broken in a hidden sector that communicates at best only through gravitational interactions. Okay, that's one black box, and this black box interacts with us through gravitational interactions. And because gravitation does not know about isospin, does not know about charge, etc., you can basically devise some universal parameters. For instance, you can basically assume universality of all the scalar masses, or all the spin 1/2, the masses of the spin 1/2 particles, and all of the trilinear couplings. And this is basically what is done. You assume that you have one mass for all the spin 1/2 particles, one mass for all the spin 0 particles, one trilinear coupling, and on top of that, you have tangent beta, and you have the sign of mu, which is the Higgs parameter, some additional parameter. And all the rest, all the soft SUSY breaking parameters at the weak scale are basically obtained from the renormalization group equations. And here you have a problem, because you cannot tune all the or not all the parameters are independent, and you cannot really tune them precisely in order to get the Higgs mass of 125 GeV. This is particularly true in models in which you have the supersymmetry breaking occurring through gauge interactions, and supersymmetry breaking occurring through anomaly mediations, through kind of fine anomaly mediation. And this is in fact clear way, because in gauge-mediated supersymmetric breaking, I mean, the fermion masses and the fermion couplings are in fact generated at the two-loop level. And in particular for the couplings, the stop mixing, in fact, it's generated at the two-loop level, and it's extremely small. It's almost zero. And that means that the xt parameter cannot be big. It's in fact zero. And in this case, because it's zero, it cannot really maximize the xt parameter that has to be square root of 6 ms in order to maximize your radiative correction. In this case, it's zero. And therefore, you need extremely large scales in order to have radiative corrections that are strong enough to make that the Higgs mass is 126 GeV. In fact, in this model, and this is basically the same also in the MSB models, in anomaly-mediated models, in fact, you also have an AT parameter, an xt parameter that is small. So, in models of this type, and let me show you what is IMSB and GMSB. IMSB is the green, and GMSB is this gray. And you see that in all cases, up to, this is for MSUSY, of course, smaller than 3 TeV, you cannot reach 123 GeV. And therefore, it's almost impossible in these minimal scenarios, because of course now you can also extend the model, put a little bit of additional matter, increase the number of messengers, etc. But there are plenty of things, in fact, to do in order to make your theory a little bit complicated. But these minimal versions, in fact, it's impossible. I mean, if MSUSY is supposed to be less than 3 TeV, it's impossible to get 123 GeV. So in fact, you can say that these models are dead. In a kind of non-fine-tuned theory. Okay, so it has a far-reaching, more far-reaching consequences in unified models. Okay. Of course, now you can say, because the main point, as I said, is the SUSY scale. The SUSY scale. It's clear that the bigger it is, the more at ease you are with the 125 TeV. Okay. And it happens that people are started, in fact, because supersymmetry didn't show up at a few hundred GeV scale, started to think that maybe, in fact, we are just getting it wrong, and this supersymmetry is not supposed to be the solution to the hierarchy problem. And in this case, maybe we should just push the SUSY scale to MGAT, and that's it. Yeah. So the first scenario that has been devised was just to push the scalar masses up to ground unification scale, to the high scale, but still keep the other virtues of supersymmetry, which is the solution to the dark matter problem. And the solution to the dark matter problem is the neutralino, the lightest supersymmetric particle, and with the proper interactions to be the good, to have the good cosmological relic density. And for this particle, in fact, you don't need to have light fermions. Only, a good mixture of gauginos and Higgsinos can make it being a good dark matter particle. And it happens that for the unifications of the couplings, in fact, only the spin and one-half particle contribute. In fact, the spin zero particle, because they form a complete fermionic, they do not make a big impact in the running of the couplings, and which make that the unification happens at the gut scale. In fact, having only the spin one-half particle at the scale of 1 TeV, the scale of 1 TeV, is enough to distort the slope of the coupling in order to make them unified TeV. So split supersymmetry is really good in the sense that it doesn't anymore address now the hierarchy problem, but it addresses the other problems. And supersymmetry is still a good that's what people say. But okay, I think for me, for me, it was fine. It was fine. It came for this hierarchy problem, so it's already giving up somehow. Yeah. Anyways, the other solution is to completely give up. And this is what people did. After once you give the hierarchy problem, you can give up the hierarchy problem. For me, you can give up everything. And people, in fact, did this step further and just said, okay, why? We should maybe just forget about everything. Supersymmetry is a good theory, but it hasn't to do anything with the low energy physics, and it's broken at the gut scale, and that's it. Okay. And in this case, still there is some the resulting action of supersymmetry in the gauge couplings. I mean, in the Yukawa time, in the quartic Higgs coupling, and therefore you can still have a prediction for this Higgs coupling in terms of the SUSY scale MS, and also for instance, you can say this is the quartic gauge coupling in the case of the MSSM at the high scale, and maybe I should show you this plot. This is in split SUSY, where you have MS of as a function of MS, you have M Higgs, and you see that for tangent beta equal 50 and the big scale of 10 to the you by far. Overshoot 125 GeV. So it's better not to have large values of tangent beta if you have big scales. So you have to make a good trade between small values of tangent beta and values of the scale. But in what we call high scale SUSY, in which everybody is at the very big scale, in fact the situation is much more comfortable, because you can have 125 GeV Higgs if tangent beta is equal to 1. And the Higgs, the scale of the ground unification scale. So in fact, people are starting to worry, to wonder whether these low values of tangent beta are not really a good thing after all. You just need to have a SUSY scale that is bigger. Okay, I think I should maybe be very quick for the two other ingredients, because I spent too much time on my introduction. The second thing that you have to do, of course, is to derive the conclusions that you get from the measurement of the Higgs couplings. And in the MSSM, remember that the couplings of the lightest Higgs, the ones that is supposed to have observed at the LHC, to gauge bosons, to up-type quarks and to down-type quarks, and the charge vectors are given by this famous formula in terms of beta and alpha, so sin beta minus alpha, these combinations. And that means that modulo the radiative corrections, once you measure these couplings, you can have a big, and alpha is basically given in terms of tangent beta and MA, the two input parameters. So if you measure these couplings, you basically have a constraint on tangent beta and MA. Modulo, of course, these radiative corrections, and also, and this is the problem, modulo the fact that in the production of the Higgs in the MSSM supersymmetric theories, you have additional radiative corrections in the production and decay mechanisms. Okay? So it's not only that the Higgs sector is described by additional parameters, it's also the fact that you have direct corrections in the production of the Higgs and in the decay of the Higgs. And this is particularly true because in the production mechanism, the dominant process is in fact gluon into Higgs. Maybe this is one of the, this is by far the dominant Higgs production mechanism in the standard model, and also the case in the MSSM. In the standard model, it's mediated by top quarks, but in the minimal supersymmetric extension in the standard model, there are also contributions from the scalar partners of the top quark. So you have stop contributions, and these stop contributions can be large. That's one thing. And the second thing is that in the case of the decays, in the standard model, the dominant decay mode is BB bar. In the MSSM, this BB bar, in fact, can have additional contribution because in the BB bar decay, you can add an additional loop in which you have a gluino and this bottom that is introduced. And this bottom in gluino, in fact, give contributions that are proportional to tangent beta. And at the end of the day, if tangent beta is large, it happens that this delta B, which is proportional to mu tangent beta, can be big, very big, and basically distort for you the Higgs branching ratio into BB bar. Okay, so you have, just to say that you have direct corrections and you have to really to care about that. So in fact, what you do, and then you have here you don't have any strong radiative corrections. So in fact, if you really want to fit the couplings of the Higgs in the MSSM, you have at least to fit 3 couplings. You have to fit the top coupling, the bottom coupling, and the coupling to gauge bosons. And you have to assume that the other ones are basically behaving more or less the same, because otherwise you have too many parameters in the game, you cannot really do a proper. But in any case, this is what people did. And at the end of the day, at the end of the day, when you do the 3-dimensional fit, this is, I don't know exactly what happened to this plot, but this is 1 sigma and this is 3 sigma, and you see that, okay, you are basically around 0. So you are more or less in a region, around 0, which means around 1, sorry. This means basically the best fit value is basically 1. Okay. So it's another way of describing the evidence that these couplings are standard model. Okay. Now, of course, if you want to go back to the MSSM, you know that in these couplings you had these additional contributions from the direct corrections. What you can say that is that these are smaller. For instance, I assume that at least in this quark sector, because I know that M-SUSY is 1 TeV, so all these additional direct corrections are small. So let me see what happens only to the Higgs sector, and the Higgs sector is basically parameterized by tangent beta and MA. And basically, in this case, that means that you have only 2 free couplings. One is basically just given by the trigonometric relation that relates to the 2 other couplings. And here you can make your 2-dimensional fit. And when you go to that fit and to the 2-dimensional fit and try to get the best value of the inputs, tangent beta and MA, the best fit values that we get is tangent beta is equal to 1 and MA equal to 500 GeV. And this is very interesting because that means that the other Higgses are basically having 500 GeV masses, and that means that basically next run the LHC, you might produce them. Now, of course, the chi-squared is really damn flat here, and any other value, unfortunately, would have given a more or less reasonable answer. So, just to say that this possibility is really good. Okay. Well, this is what you do for the fits, and afterward, depending on how confident you want to be, you see that in fact masses MA smaller than 250 GeV are basically excluded. Okay. So just from the measurement of the couplings and the assumption that the SUSY scale is heavy enough, is big enough, in fact it's clear that you cannot have any values. The third thing that you have to do is this I will go quickly, is to search for the heavy Higgses that are predicted by the theory. And for this, in fact, you have to look for the heavy CP even and CP odd states and for the charged Higgs states. And at the end of the day, in fact, what happens is that there are only 2 mechanisms that are important in this game. Gluon-gluon fusion, and then in which, in fact, not only the top quark loop contributes, but also the bottom quark loop, because remember that this pseudoscalar and this heavy Higgs is coupled to bottom quarks proportionally to tangent beta. So for high tangent beta, the coupling to B quark is extremely enhanced, while the coupling to top quarks is extremely suppressed. And therefore, you have big cross-sections, in fact, much bigger than in the standard model if you have enough large values of tangent beta. And also, in the production in association with heavy quarks, rather than putting only the top quarks, you have also to put the bottom quarks. And with these enhanced couplings and with the gain that you make in the phase space, you can really, in fact, increase the cross-section by large amount. So the main dominant contributions are, in fact, glue and glue into BB bar Higgs. And for the charged Higgs, you have the possibility, of course, of obtaining it, if it's light enough, from top decays. So you have a top, you produce millions of TT bar pairs, a top that decays into a B and charged Higgs, and the charged Higgs goes into a tau and neutrino. So basically, you look at lepton number, lepton flavor violation, if you wish, because you have a little bit more taus than muons because of this additional charged Higgs decay. So it's the process that you have to look for. In particular, at high tangent beta, all these neutral guys in fact decay into BB bar and tau tau with a branching ratio that is 90 and 10%. Okay, this is what happens at high and for the charged Higgs, in fact, the only decays is into tau nu or TB. This is what happens at high tangent beta values. But of course, now if you prefer the low tangent beta issues, then the situation becomes more complicated. The couplings to gauge bosons, for instance, of the heavy Higgs are not suppressed, so you can still have the Higgs decay into WW and ZZ, like in the standard model case, although they are still a little bit suppressed. And then at high masses, you have the possibility, of course, of the heavy guys decaying into BB bar, TT bar. So that's become new dimension. Okay. Bon. Not make the story long. Of course, all these channels have been searched for. In particular, the search for tau-tau resonances. So in fact, what happens is that you produce the H, capital H, and the A through glue-glue fusion, for instance, or BB bar fusion, and you make them decay into tau-tau resonances. And when you interpret that in the MSSM parameter space, you see that in fact it's a very, very strong constraint. In fact, anything below tangent beta equal 5, for instance, is ruled out if the pseudoscalar mass is less than 300 GeV. So it starts really to be extremely, extremely, extremely powerful. For the charged Higgs, in fact, because you had so many TT bar pairs and you measure, any additional decay mode would have been observed. Then in fact, it turns out that with the 25 inverse femtoband data, 20 inverse femtoband data that have been collected at 8 TeV, you can basically rule out all the scenarios in which the charged Higgs mass is lighter than the top mass. Something like lighter than 160 GeV, and only a few corners are left. Now, the other thing that you can do, and that CMS and Atlas didn't start yet to do, is really to take advantage of all the searches of the heavy standard model Higgs particle that has been performed in the past. Because, before we didn't know the mass of the Higgs, so you needed to make sure that we will discover it, and to make sure that we will discover it, you have really to, probe the entire possibilities for the Higgs mass range, and of course the Higgs mass went up to 708 GeV to 1 TeV. Okay, so people looked at the WW final state, ZZ final state, etc. And this, in fact, of course, now you cannot do it anymore for the standard model Higgs, but you have to do it for all the Higgses that could be heavier than standard. Additional Higgses in any type of model, for instance, in the MSSM, or in 2 Higgs doublet models, or in any scenario. And the limits that you have on standard model Higgs, in fact, you can interpret them in terms of in the context of your own model. Now I have I have some complaints about what Atlas and CMS are doing for the moment, because in this benchmark, you remember, tangent beta MA, in fact, in the parameter space, in fact, you don't have if you have low tangent beta and low MA, the Higgs mass is so small, the observed Higgs mass is so small that your parameter space is basically useless. Okay, you have a Higgs mass of 120 GeV, less than 120 GeV in most of this parameter space. So it's really annoying, in fact, in the parameter space that you are probing directly. Everything is ruled out by just the mass of the other Higgs that you have observed. And for this, we have, in fact, a good way to evade this possibility is, in fact, to trade. You remember that you know, in the leading part of the radiative corrections was something that is basically only affecting the one entry of the 2 by 2 matrix that describes the radiative corrections. In fact, in this dominant, in this situation where there's only one dominant piece in the radiative corrections, you can trade this radiative corrections against the measured value of the Higgs mass. In fact, you can basically say, okay, I don't care about the SUSY parameters, I just change this radiative corrections against the Higgs mass. So I come back, in fact, to my original 2 parameter space, like it was at 3 level, you know, MA tangent beta, but now with the radiative corrections fixed by the fact that the Higgs is equal to 125 GeV. And automatically, in any time, you can obtain, of course, the masses of the other Higgses, you know, MH, capital H, alpha, MH plus, and in all this, when you use all this formula, in all the parameter space, in fact, you have automatically M Higgs fixed to 125 GeV. Okay? Of course, this only works if there is only one component of the radiative correction, so it works only in this dominant case, in the case where the dominant radiative correction is only one entry in the 2 by 2 parameter space. But in fact, we have checked it. When you vary all the other parameters of the MSSM, that the approximation is not there. And if you do that, then things become interesting, in fact, because you can really now take all the other channels that you can, that have been used for the standard model or that have been used for many extensions, and use them, in fact, in this low area of the parameter space. In particular, you can use, for instance, Higgs into WW and Higgs into ZZ in order to constrain the low tangent beta parameter space. Because you see, the high tangent parameter space is basically covered by the Higgs decays into tau tau. Here, in fact, you use all the other channels, in particular WW, ZZ, this HH, for instance, there is the possibility of producing, where is it? Producing the heavy Higgs and make it decay into 2 light Higgses, the production of a pseudoscalar that goes into HZ, and this gives you a probe of the entire, the low tangent beta parameter space. And the most interesting part is that, in fact, you can also probe this low tangent beta parameter above the TT bar threshold by looking at TT bar final states produced by HE. So my bet is that at the end of the day, if you have, for instance, high energies, higher luminosities, you will probe more and more parameter at high tangent beta by this Higgs into tau tau analysis. And with TT bar and the other channels, you probe the low tangent beta area. And at the end of the day, you just, when you increase the statistics and you increase, the energy and the luminosity, these 2 areas can overlap, if you wish, at higher and higher values of pseudoscalar mass. So basically, you are probing the entire parameter space directly, and not only through indirect means, etc. And at the end of the day, you are sure, in fact, that you closed basically all the possibilities for an new state. Okay, so I think I should stop here. Sorry for took a little bit more time, but my point is that it's still we have still 1 year to go. But that's by it's still action time, so we should not give up. In particular, for the precision measurements, something might show up. It was of course when the Higgs was produced, it was a little bit annoying that. Although in the beginning, the biggest news, in fact, when in December 2011 or even in January, in July, when the Higgs was, it's not the discovery of the Higgs. If you look at Spiers, the fact that triggered the biggest number of papers is the gamma excess. Okay, so the fact that there was a deviation from the standard model expectation. Okay, now of course this one went away, but still they have a 20% uncertainty. So maybe if you measure things with a 5% precision, you can maybe get a 10% discrepancy. So still we have to go on with this. Yeah. And now, of course, you have to keep searching for the heavy Higgses. In particular, I gave you the best fit for the MSSM Higgs sector, which is tangent beta equal 1 and MA equal 500 GeV. So you have to really go and search this beast at this high scale. And of course, you have to keep searching for in particular, for the weakly interacting supersymmetric particles. Maybe they just have a few hundred GeV and they are around the corner. So we should really wait. Maybe next year something will happen and the trend will completely change, because now, for instance, I see that everybody is starting to be a little bit nervous, even a little bit depressed, maybe next year things will completely change. Thank you.